Let's say you open up a navigation app and ask for driving directions from New York to San Francisco. Between those two coasts, the North American road system contains over 64 million distinct intersections. If you try to calculate the absolute shortest path by brute forcing it, there are roughly 10 to the 220 possible routes. Even checking a billion routes per second, finding the best one takes over 10 to the 200 years. But when you actually type that destination into your phone, you get a perfect route back in just a few seconds. The actual computing time for that search is usually less than a millisecond. Since checking every road is a physical impossibility, modern software isn't brute forcing the math. It bypasses the vast majority of the continent using a series of mathematical loopholes. The foundation for these loopholes dates back to a shopping trip in Amsterdam in 1956. A programmer named Edsger Dijkstra needed a way to prove that a new computer called Armac was actually useful to the public. Without using a pen or paper, he designed a pathfinding solution in his head in about 20 minutes. His method, now known as Dijkstra's algorithm, starts at a source and explores neighboring intersections, or nodes. It calculates the distance, or the cost, to each one. It locks in the shortest path to a close node, then builds off that to find the next one, guaranteeing it finds the shortest overall route. But to maintain that guarantee, the algorithm explores outward in all directions simultaneously. If you want to go west, it still checks every road going north, south, and east, expanding outward like a growing circle. When applied to the entire North American road network, exploring all those illogical directions means the algorithm has to check nearly all 64 million nodes. Even highly optimized, a single search takes about 7 seconds. 7 seconds sounds fast, but server farms process millions of navigation requests from other users at the exact same time. A queue of 7-second tasks creates a massive bottleneck. The software needed an upgrade. The first major fix was a modified algorithm called A*. It introduces a heuristic, a mathematical rule that penalizes routes heading in the wrong direction. By treating nodes further from the destination as if they are sitting on an upward slope, A* aggressively targets the correct area. While this works perfectly for minimizing raw geographic distance, it struggles when you want to minimize travel time. Factoring in varying speed limits requires complex square root computations, which actually forces A* to evaluate more nodes than a standard Dijkstra search. To speed things up without complex penalties, engineers tried running the search in both directions at once. By expanding outward from the start and the destination simultaneously until the two search radii intercept, the algorithm halves the required work. Yet neither of these patches understands how human beings actually drive. To these algorithms, a twisty local road and a massive multi-lane interstate carry the exact same weight if their distances are equal. They will happily search a tiny cul-de-sac while looking for a cross-country route. Purely mathematical searches hit a performance wall because they cannot comprehend the physical hierarchy of the world. The ultimate solution is a technique called a customizable contraction hierarchy. Instead of forcing the live search to figure everything out on the fly, engineers pre-process the entire map to identify the most critical physical bottlenecks. A computer mathematically cuts the continental map in half, looking for the smallest number of roads that connect the two sides. This highlights massive natural barriers, like the bridges crossing the Mississippi River, and ranks those specific intersections with the highest possible priority. It then splits the remaining halves again and again, ranking every single road. With all 64 million nodes ranked, the Life search algorithm is heavily constrained. It is only allowed to look up the hierarchy, jumping straight from local streets to higher-tier interstates using pre-calculated shortcuts, entirely ignoring the residential roads nearby. By reducing the search space to a tiny fraction of the continent, the query runtime drops from 7 seconds to about 200 microseconds. By translating the physical realities of geography into ranked data, engineers eliminated massive amounts of computational waste, dropping the required search from tens of millions of intersections to a little over 1,000. When you tap Go on your phone today, you get an instant result because of this aggressive, hierarchical filtration process. But underneath the pre-processing, the heuristics, and the custom shortcuts, the actual engine executing the search is the exact same algorithm Dijkstra published decades ago. Dijkstra believed that simplicity is prerequisite for reliability. Because he designed the method entirely in his head, without a pen, he was forced to strip away any avoidable complexities. Almost every major development in modern pathfinding relies on the foundation he conceptualized on a cafe terrace in 20 minutes. The incredibly dense, massive problems of the modern world rarely demand infinitely complex solutions. They require impeccably simple fundamentals that can scale forever.